Today is going to be covering, continuing Newton's second law equations, or equations of motion, where we have forces or unbalanced forces causing acceleration. And we're just going to extend what we did on Tuesday. We're going to revisit, I guess, normal, tangential coordinates and cylindrical coordinates. So if you thought we were done with that before, we got more to do. So we have another chance to look at those coordinates and do some more problems. So let's start off with our reading quiz. The normal component of the equation of motion is written as this equation here: sigma Fn is equal to m times An, where sigma Fn is referred to as the what? The impulse, the centripetal force, the tangential force, or the inertial force. B, 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 B. Lots of B's. Good. Good, that's correct. So the normal force that we feel when an object is undergoing centripetal acceleration, which is An, would be called a centripetal force. Good. So let's look at normal and tangential coordinates again. So when a particle moves along a curved path, just like we had discussed when we're just talking about motion and kinematics, we had written a coordinate system that moves with that particle, and we defined a tangential coordinate, a normal coordinate, and then we also defined a binormal coordinate if we had three-dimensional motion. So here we have our tangential, normal, and binormal. And so if we have our equations of motion, just like we did before, we would notice that the particle is always moving along the curved path, and we have two components of our acceleration. One was our tangential acceleration, and one was our normal acceleration. And we can apply those to the exact same equations of motion in Newton's second law that we always had before. So again, just to reiterate, normal direction, same as before, always points towards the center of curvature. And likewise, the tangential coordinate, or the tangential direction, is always tangent to the path and positive in the direction of motion. So the tangential direction is always tangent to the path, and it's positive in the direction of motion of the particle. So let's write our equations of motion. If we first recall that if we know the path, if we're given a problem where we know the path as a function y equals f of x, that should be a good hint that maybe we should be looking at normal tangential coordinates. And if we do know that path, we can figure out the radius of curvature anywhere along that path using this equation, which is what we had from our kinematics. So let's write our equations of motion now. So just like we did with our straight line coordinates or rectilinear coordinates, Cartesian coordinates, we can write the sum of the forces is equal to the mass times the acceleration of the particle. And we can break this, just like we did before, into our components. So our three component forces can be our tangential force times our tangential unit vector plus the sum of the force in the normal direction times the normal direction unit vector plus the sum of the force in the binormal direction times the binormal unit vector is all equal to our mass times our tangential acceleration plus our mass times our normal acceleration. Now notice there's no binormal acceleration because by definition, there's no motion in and out of that plane. So if we isolate these and put them in component form, we can get some of the forces in the tangential direction is equal to ma times the tangential acceleration, or m times the tangential acceleration. And some of the forces in the normal direction is equal to the mass times the normal acceleration. And that third equation would just be some of the forces in the binormal direction are just equal to 0. There's no acceleration.
Excuse me, sir.
Yeah.
Could you explain binomial? Like what exactly is that?
Okay, so if we imagine, try and crudely draw, there's some plane that this object is moving in. So imagine that this curve rests in this green plane. The b direction, the binomial direction, is the direction that is normal to that plane. So it's perpendicular to both the normal and tangential directions, and it sticks straight out of the plane of motion. So if that object is moving within that plane of motion, that plane could be oriented whichever way in three-dimensional space. If it stays in that plane for some small period of time, that means there's no acceleration in that direction, which means that the sum of the forces acting on that particle in that direction must add to 0.
Okay, I see. It's just they just use the b to avoid confusion with the normal force.
They use the b. I'm not sure why they call it b. They call it binormal just because it's normal to both of the other coordinate directions. So it's normal to the normal direction and it's normal to the tangential direction. Normal just means perpendicular here.
Okay, I see. All right, thank you.
Yeah, all this direction is defining is the plane of motion. So when we're dealing with 2D problems, that plane of motion is just that third plane that would be in or out of the page if we're viewing a 2D problem. It comes more into play with 3D problems when you're dealing with rigid body motion of maybe a mass, not just a particle, but a mass that could also spin and rotate. But for particle motion, typically we can break it down to 2D problems. So our procedure for analysis when we're looking at solving these problems with curvilinear coordinates, and when we're dealing with normal and tangential coordinates, it's good to keep this in mind. So when a problem involves the motion of a particle along a known curved path, I would say this is the important thing. If you have a known curved path as a function, then that should be a good hint that normal and tangential coordinates should be considered. The other thing I would say is if you also know something about the speed of the particle, and you know something about the radius of curvature that the particle is undergoing. So knowing the curved path would be knowing the radius of curvature. So to solve the problems, you always need to include a free body diagram. So in your free body diagram, you'll establish the coordinate system that you're going to choose, and it's going to be located at the particle for the nt coordinate system. The particle's normal acceleration is always acts in the positive n direction, or positive an is in the positive n direction. If an is pointing opposite of the n direction, then it's negative acceleration. If the tangential acceleration is unknown, assume it acts in the positive direction. And there is no acceleration in the b direction. And then after you have your equations or your free body diagram, it becomes easier to write your equations and you can solve for your unknowns using the equations of motion. So let's look at an example. So in this question, it says, determine the banking angle theta for the race car track, the racetrack, so that the wheels of the racing cars will not have to depend on friction to prevent any car from sliding up or down the track. Assume the cars have negligible size, a mass m, and travel around the corner of radius of curvature rho with constant speed v. So our first step is always going to be that free body diagram. So for our free body diagram, what we'll do is we'll draw our figure, or in this case, it's going to be a car, and it's going to be inclined at some angle theta. So if it's going around a track, let's draw our car, one wheel. Here's another wheel. Maybe we have a wing at the back, or something. And we'll draw our center of gravity somewhere around here. And then we can start labeling some points. So our forces acting on the car will be our weight. And that's going to be acting right through the center of gravity. And that would be equal to mg. And then the other force we have acting on the car is our normal force. And that's going to be acting at some inclined angle. Theta. And then lastly, we have to draw our coordinate directions. So I'll draw those in green. Our coordinate directions will be our normal direction. And in this plane, what we can see is our binormal direction. So our tangential direction here is going to be in and out of the page. So if this is our free body diagram, we can also draw our kinetic diagram. So in our kinetic diagram, we're going what accelerations? Where is our acceleration going to be?
Would the tangential
pointed
one
in the
be
normal
in and
direction?
out?
Yeah, so there would be a normal acceleration, and that would be acting in the positive n direction. There's no binormal acceleration by definition. And in the tangential direction, there could be if the car is speeding up or slowing down. But the question says that the car is traveling at a constant speed v. So it says constant speed, and our a tangential, we know from our kinematic equations, is just equal to v dot. That means that our speed isn't changing, so this is equal to 0. So there's no tangential component to acceleration. So we have our diagrams, we have our free body diagram, we have our forces, we have our geometry, we have our coordinates, and we have our kinetic diagram. So now let's write our equations of motion. See if we can keep some of that in the picture. So let's start with our forces in the normal direction. And as we've drawn it up above, this is our positive direction. So they're equal to our mass times our normal acceleration. So the only force we have acting with a component in that normal direction would be our normal force times the sine of the angle between that and the vertical. So we have n sine theta, and that is equal to our mass times our normal acceleration. And we can write our normal acceleration in terms of our velocity, which is v squared over rho. So that's our first equation. Our next equation we can write some of the forces in the binormal direction. And we know that positive direction is upwards, and this must be equal to 0. There's no acceleration up or down off the track. The car's not flying away. And so our components here, we have our normal force times cos theta acting upwards, and we have our weight, which is mg, acting downwards, and this is equal to 0. So if we eliminate n, we can do that by taking equation 2, moving mg to the other side, and then dividing equation 1 by equation 2. So let's do 1 divided by 2. And if we do this, this would give us tan theta is equal to v squared. Our m's cancel out, and we're just left over with gravity times rho. So therefore, theta is just equal to the tan inverse of v squared over g times rho. Good. So let's go back and ask one more question. Yeah, maybe you have a question for me.
Okay, so I just wanted to see, like, the normal force, the sine component of that is the same as the normal force?
So the normal force is going to
No,
act.
like the one that goes what do you call it? Like towards the center of the curvature is what I'm talking about. So like
Okay.
so n is the normal force, right? Or
Yeah, this would be
sorry,
confusing and important. So let me go back here.
Yeah.
Let's pretend this blue line here is the track.
Mm-hmm.
So when we talk about normal force is just what has been defined as the force that is reacting to the force of gravity when an object is resting on something.
Okay.
So in this case, our normal force, capital N, is an external force, and that's the force of the ground pushing upwards on the car, and it's just counteracting gravity, or it's counteracting all the other forces. It's just a reaction of something resting on the ground.
Mm-hmm.
And it's different than the component of the normal force in the normal direction. So because our coordinates are called normal and tangential, I could just call this a reaction force instead. Maybe we'll call it R.
Okay.
And then if this is a reaction from the ground, the component of a reaction that's in the normal direction, as in the component that's pointing towards the center of the radius of curvature, would be the component of our reaction force in the normal direction.
Okay. Yeah, and sorry, I think I questioned my like I worded my question wrong. It's just so the N, the capital N, right? That force is the same as like mg sine theta, right? Would it be?
Yeah.
Okay, so that's okay, I see. Okay.
Not quite.
No? Okay.
See, if we look at equation 2 here, if we rearrange this, you could find that N is equal to mg divided by cos theta.
Okay, so it's different. So like for example, if we just had like no curvilinear motion and we just had like a slanted plane, if we do have a normal force that's reacting against it, then that's the same as mg cos theta. But then what do you call it? For this one, it's not the same because it's curved. There's a curvature.
It's different because we have a normal acceleration in this direction here. So if we had a perfectly static system, so it wasn't accelerating, if AN didn't exist, so we had just had the car resting on that plane, on that slant, and it had to stay still, what we would have is we would have some sort of frictional force. So the car would want to slide downwards, we want to go this way. So we have to apply there would be some frictional reaction force.
Okay, okay, I see it now. I see it now. Okay.
This would be our force of friction.
Yeah.
The question is asking, we're driving at such a speed now that there is no frictional force. It's not relying on that. So that means that the only forces that are still there, gravity and the normal force from the road, must be equal to that normal component of our acceleration, AN.
Okay. All right, I understand now. Thank you.
Okay. So let's do another example. So in this example, we have a 3 kilogram disc is at D, and it's attached to the end of a cord. The other end of the cord is attached to a ball and socket joint located at the center of the platform. So the ball and socket joint is just freely rotates. If the platform rotates rapidly and the disc is placed on it and released from rest, determine the time it takes for the disc to reach a speed great enough to break the cord. The maximum tension in the cord must sustain 100 newtons, and the coefficient of kinetic friction between the disc and the platform is mu k is equal to 0.1. So first, before we try to solve anything, let's try to imagine what's happening here. Who can describe what's going on in this problem?
Basically, you will have like something rotating and then giving like you have like something down. I imagine because it's similar to an upright where you have like a weight down and causes the thing to rotate.
Right, so we have this platform and the disc is just resting on it. And let's imagine that we're holding that disc still and the platform's just spinning underneath it. So it's like we're dropping the needle on a vinyl record.
Yeah, essentially, yeah.
So then there's friction between the disc and the platform that's rotating. We're going to let go of the disc now. And that friction between the two is going to cause that disc to accelerate. And that's going to accelerate around the center of the platform because it's held in place by that cord and that ball and socket joint. And it's going to speed up and speed up and speed up. And the question makes it seem like we can assume the platform is always moving so fast that it's always sliding. And then we are asked to find how long will it take for that disc to speed up enough that the centripetal force acting on that cord will actually cause it to break, and the cord can only withstand or sustain 100 newtons of force before it breaks. So if we know that, let's start by drawing our free body diagram. So let's just look at our disc, and let's try to draw it at the moment that's shown. So our FBD. Here's our disc. Let's do better than that. Here's our disc. We have our tension force that's acting in our normal direction. And we have a force acting in the tangential direction. And this would be the force due to friction that's causing it to accelerate. And that's in the tangential direction. We have a normal force acting upwards. And we have a force of gravity, which is the weight, acting downwards. And this would be our B direction. So this is our free body diagram, our kinetic diagram. Draw our disk again. We should have two components of acceleration this time. We have one which is acting in the tangential direction, and we have one acting in the normal direction.
Why is the force of friction not in the opposite direction of the motion?
So this could be, yeah, let's look at that a bit more. If we look at the disk image over here. So when we release the disk from rest, the platform underneath is rotating in this direction. So what is the direction of sliding of the disk relative to the platform? Is the disk moving clockwise or counterclockwise relative to the platform?
Clockwise, right?
Right. So if the disk relative to the platform, the direction of sliding is clockwise, that means the force of friction acting on that disk must be counterclockwise.
Gotcha.
So that's why I like to make that definition from Tuesday. Instead of friction isn't acting against the direction of motion, it's acting against the direction of sliding. And then sliding is always relative motion. So if we have a case like this, if that platform is always moving faster than that disk, then the disk's sliding is always counterclockwise relative to the platform. So that force of friction is always going to be acting counterclockwise in the direction that the platform is moving. So we have our free body diagrams. Now let's write our equations of motion. Let's start with our normal acceleration again. Sum of our forces in the normal direction are equal to MAN. So in the normal direction, the only force we have is T, our tension. That's in that cord. And our mass and their acceleration is 3 kilograms mass, and normal commotive acceleration would be v squared over rho, and it says in the diagram that rho is 1 meter. So we have 3 kilograms times v squared over 1 meter. Our next equation, let's look at the transverse direction, or tangential direction rather. So in the tangential direction, we have our frictional force. And in this case, our frictional force is just equal to our coefficient of friction times ND. So 0.1 times, our normal force, N. And this is equal to 3 times our tangential acceleration. And then our last equation, FB, some of the forces in the binormal direction are equal to 0. So we have our normal force minus mg is equal to 0. So these are our three equations. So if we solve these, for our unknowns, we should get our normal force is equal to 29.43 newtons. Well, that looks confusing. N is equal to 29.43 N. We've created some new math that I don't even know. So let's add a subscript for these so we know they're normal force acting on the disk. And when we look at this later, it won't give us so much confusion. All right, so our normal force is 29.43 newtons. Our tangential acceleration is equal to 0.981 meters per second squared. And the velocity, we'll call it our critical velocity. So when we have braking, is equal to 5.77 meters per second squared. So that's the velocity when t is equal to 100, or equal to 100 newtons. So we're almost done. It asks us, how long is it going to take for that cord to break? So what equation of motion can we use? Or what kinematic equation can we use to solve this?
V squared equals V initial squared plus A delta T.
Not squared.
V equals V naught plus ACT.
Right, so we have our velocity at the end that we want, our critical velocity would be equal to our initial velocity, which we said is just starting at rest, so that's just equal to 0, plus our tangential acceleration times t. So if we solve this, we should get t is equal to 9 seconds. Good. Let me just back out. I'm trying to give my iPad another break before we go into another example. All right. Third example, we have the design of a ski jump. Requires knowing the type of force that will be exerted on the skier and her approximate trajectory. So we don't want to have the curvature at the end of that ramp be so great that they just sort of collapse down. They can't withstand the centripetal force. So in this case, the jump can be approximated by a parabola. Determine the normal force on the 150-pound skier the instant she arrives at the end of the jump, point A, where her velocity is 65 feet per second. And it also asks, what is her acceleration at this point? So in this case, we have an equation for the path. So that should be a hint that this might not be obvious at the beginning, but we have an equation for the path y as some function of x. So we can use this to determine our radius of curvature, and we should use n and t coordinates. So let's do our free body diagram. Let's pretend we have our skier. There's our crude little skier. And we got our arms back, ready to jump. And the forces we have acting on that skier is a normal force. Call this NA. And this is and we have the weight of that skier, which is 150 pounds. Remember that pounds is a force. So we already have our weight, it's given to us, 150 pounds. And our normal direction, we actually don't know what our normal direction is yet. I guess it's perpendicular to the path, so let's draw it here. And we have our tangent direction. We're just assuming that this is all upright. We have to figure that out for sure. And then our kinetic diagram, this time we'll just draw on the same diagram, so I don't have to try and draw another skier again. Let's draw in a different color. We'll have our normal component of acceleration and our tangential component of acceleration. So we have our free body and kinetic diagram sort of merged into one this time. We have all the forces. We just have normal force from the track, or the jump acting on the skier, and we have the weight due to gravity. What should we do next?
Should we find the normal and tangential directions?
Yeah, we could do that. How do we find that?
Isn't it the tan inverse of dy by dx?
Yeah, that's one method. One method that I like to use is if we actually just look at the derivative, so dy dx, that just gives us the slope. And if we find the slope of the line, the negative reciprocal of that slope, or the inverse of that slope, would give us the perpendicular direction. So what I mean by that is our path is y is equal to 1 over 200 x squared minus 200. So our slope, dy dx, is equal to 2 over 200 times x, so 1, or x over 100. And then our constant term goes away. And so right here in the diagram, it looks as though we are solving for the position where x is equal to 0. So that looks like it goes through right through point A, according to that diagram. So if we solve for our slope at x is equal to 0, then our slope is just equal to 0. So that means our tangent direction is horizontal, and then our normal direction must be perpendicular to that, so our perpendicular direction, normal direction, is vertical.
I have a quick question, Professor.
Yeah.
Just wondering, does it really matter the directions here though? Just because like it's when we're doing the FBD for an instant in time, so
Yeah.
what we're really using is basically the formula for the radius of curvature and then the other forces we have. I was just wondering, like,
Yep, so the only reason that we would have to figure out what the actual slope is because we need to know which direction gravity is pulling the skier.
oh, okay, that makes sense. Thank
So
you.
gravity is always going to be acting in that vertical direction. And if the skier is jumping from somewhere else, maybe they're jumping from, the ski jump continues and jumping from over here. Now gravity is in this direction and our normal direction's over here. And we might have N is in this direction, T is in this direction.
No, that actually makes sense. Okay. Thank
So
you.
we only needed to know the direction of that gravitational force. And because it's right at the bottom, it actually works out quite conveniently that we don't have to worry about any angles. So we have T is in the horizontal direction, N is vertical. So we can write our equations of motion. Some of the forces in the normal direction equal to MAN. So our upwards normal NA minus our weight 150 is equal to our mass. So our mass now is going to be 150 divided by acceleration due to gravity, 32.2 feet per second squared, times our velocity, which is given in the question as 65 feet per second squared, divided by rho. So that's our first equation. Next, our tangential forces are equal to our mass times our tangential acceleration. So our tangential forces, we don't have any. And that's equal to our mass times AT. And since our mass is not zero, that means AT must be zero. So the only component of acceleration that we have is our normal acceleration. But to find our normal acceleration, we need to figure out what our radius of curvature is. So let's use that equation from before. Ooh. So our equation for rho is 1 plus dy dx squared, all to the power of 3 over 2, divided by the absolute value of d squared y dx squared. And we're going to evaluate this right at that point where the skier is, which is when x is equal to 0. So our derivative, dy dx, is x over 100. So we know our first derivative. So we have 1 plus x over 100 evaluated at x equals 0 is just 0. And our second derivative is just 1 over 100. And at x equals 0, it's still a constant, so it's just 1 over 100. So we end up with the numerator is just 1, and it's divided by 1 over 100, so it's just 100 feet. So finally, we can say our normal force is equal to 347 pounds. Solving equation 1. So that's the force that skier will feel from the ramp pushing back. And our normal component of acceleration is our total acceleration because we have no tangential component. So A is equal to AN, which is equal to V squared over rho, 65 squared over 100, or 42.2 feet per second squared upwards.
Sir, could you go back to your diagram after you're done writing?
Yeah.
Okay, so I think I just have like a concept wrong. So okay, so the capital NA force, right? So let's say we just have let's say I have an object that's sitting on a desk, right? So I have the force of gravity and then the normal force acting upwards. So the normal force is equal to the force of gravity that's acting on the object, right? Because they cancel each other out.
If that's the only force.
If that's the only force, okay. So in this case, now there's an object that's moving, right?
Right.
So it has some acceleration that's tangent to the path and then some acceleration that's normal to the path, or
Right.
normal as in towards the center of curvature.
Yes.
So because it's in motion and because there's other accelerations on it, we can declare that the reaction force due to gravity is not equal to gravity, right? Or the weight.
Right. So our normal force is always just going to be a force that we draw in our free body diagram, which is a reaction.
Okay.
Because we have we're contacting some rigid surface or something like that. Two bodies that are contact each other have some normal force between them, and they act perpendicular to the point of contact. We can only find that normal force by writing our equations of motion. And often, if we just have maybe an object sliding on a surface, it's not accelerating in the direction of that normal force. Then if we sum of the forces in y direction for just a block sitting on the ground, say, we can usually just find out that that normal force is equal to the force of gravity, because those are the only two forces acting in that y direction, so they must be equal if we don't have any acceleration.
Okay, I see. So that the acceleration changes the force the object feels, the reactionary force the object feels then.
Right. That acceleration is due to an off balance of forces. So if it's accelerating upwards in that normal direction, over here, if it's accelerating upwards in that normal direction, that means that normal force must be greater than the weight of gravity. Otherwise, it would either just continue in a straight line or it would keep falling downwards.
Okay, thank you. Yeah, my concept about it was wrong, but you clarified it, so thank you for that.
Yeah, so don't think of normal force as just the opposite of gravity and the opposite of the weight. Normal force is not that. Normal force is just a reaction force between two bodies in contact. And the normal force from the skier pushing on the ski slope or the jump would be equal and opposite to the normal force from the ski jump pushing on the skier that we just calculated. And that normal force you calculate by using your equations of motion. And it's just a force that shows up in our equations of motion, and we solve for it just like any other force. So yeah, so in this question, our skier would have a normal force pushing upwards of 347 pounds. So if the skier weighs 150 pounds, that means that it would feel like at the bottom of that jump, her weight has more than doubled. And that's because her upwards acceleration now is 42.2 feet per second squared. So that's she's accelerating upwards against gravity more than the acceleration due to gravity, 32.2. So 10 feet per second squared more.
Okay, and I see it now because of the first equation. It says NA minus the weight. So if there was no acceleration, no AN, then in that case it would equal 0. Then in that case, NA equals 150, which
exactly. Yeah.
Okay, I see it from the equation now. Okay.
Yeah, if we're ever in doubt in questions like these, or in this course, or just in dynamics in general, I find if you draw your free body diagram correctly, then trust the math. You write out the equations, trust what the math is telling you. The math is usually right. And then once we get an answer, then we can go back and look at our answers, bring it back to our problem and say, okay, does this answer make sense? Is the math telling me, can I make sense of it? Once we get to our answer. That's how I like to tackle these kinds of problems.